of the podcast, we will discuss some common statistical scenarios in basic science. So, scenario 1. I would like to compare the levels of a protein X in the heart of two different groups of mice, one transgenic and one wild type, and I have, let's say, 10 animals per group. How do I go about this?
Okay. Going back to our suggested timeline, we will have a look at a number of considerations in all the scenarios we're going to talk about. And we're going to concentrate primarily on the design, data analysis, and interpretation, but we will not touch the research question and publication on this side. I think that's fair enough for the questions you're asking me. Let's go and see what do we know. We have one parameter of interest, you said, and that will be the level of protein X. And our population will come from two groups, two independent groups in this case. But how big are the groups? You mentioned there will be 10 animals per study, per group rather, and which means that's a rather small sample size. And I think we can safely say that our data will not be normally distributed. Therefore, we should be looking for a non-parametric test, a choice of non-parametric tests. Go back to the table that helps us decide what test to do when. Let's see how we can find out what test will be appropriate. To recap, we have two independent groups to compare, and our data is not normally distributed. So looking at these decision lines would lead us to the Mann-Whitney test.
And what happens if I have a third group?
Okay, I assume it's the same size?
Yes.
Small size. Okay, let's have a look now at the possibility of adding another group. Will be the transgenic 2. We will keep the wild type as the single group there. And all other things equal. Let's go back to the statistical test table. We now move on to see where we have 3 independent groups to compare. Again, we are staying with the non-parametric tests. And following the decision line, we can be guided to the Kruskal-Wallis test. I'd just like to say here that this test will give us a significance level considering all 3 groups at the same time. If the overall Kruskal-Wallis test is significant, that means that at least one of the pairwise comparisons between the 2 groups is significant. But at this stage, we don't know which one. So we can now go ahead and explore these individual relationships one at a time. As we are doing that, we are changing the type of test we're doing because we're back to having 2 groups to compare at a time. And we're staying with a non-normal distribution, and this time we're going back to have a number of Mann-Whitney tests to do. So let's have a look in practice what that means. When we have 3 groups, we will be testing the same hypothesis more than once for pairwise comparisons. So it's important to remember to correct for these multiple comparisons, and here we were going to have 3. In other words, we're going to be doing 3 different Mann-Whitney tests, and we will do well to don't forget to use the Bonferroni correction for multiple testing. Let's have a little bit of a reminder of how this works. In the presentation earlier, in part 2 of this podcast, we show you how to modify the chosen alpha for determining the significance level. A mathematically equivalent way of using the Bonferroni correction could work as follows. As we have 3 groups, we could adjust the p-value from each of the tests by multiplying it by 3, while we'll still use the usual critical value of 0.05 that we chose earlier, if that's what we preferred. And this multiplication by 3 means that we're adjusting by a factor of 3. So let's see how this works in practice. Say that from the Mann-Whitney test 1, we had a p-value of 0.016, which in this case is significant. If we adjust the p-value for multiple testing, we multiply this by 3, we will get 0.048. And this value is still lower than the 0.05 critical value for significance, and therefore our result in this case is significant. Say now from the Mann-Whitney 2, we've got a p-value of 0.08, which is still significant. If we adjust the p-value, multiply that by 3, we get 0.06, which in this case has gone to be not significant. In fact, this is perhaps what happens in practice more often than not when we have multiple testing situations. So let's have a look at the third case. Say from Mann-Whitney 3, we got a p-value of 0.4. If we adjust this and multiply by a factor of 3, we will have a p-value of 1.2. But in fact, this is impossible. We cannot have a p-value to exceed 1. This is because a p-value is actually a probability, and therefore we cannot have a probability that exceeds 1. In this case, what we do is we round everything down to 1. Unfortunately, in many high-impact papers, we often find that results were not adjusted for multiple comparisons. If you're alert to this issue, you could make your own inferences for the significance of a result, regardless of the claims of the paper, so bear that in mind.
Scenario 2. I have a cell culture experiment in which I have 5 wells of cells. I keep one as a control, and I treat the other 4 with an intervention for 24 hours. Then I want to compare the expression level of a protein X, between the different wells.
Let's have a look and make a recap of what we know. Again, we have one parameter here, the levels of protein X, and we will get our population from cell cultures originating from just one well, so they're going to be divided further to have a total of 5. The important clue here is that all wells are related to each other. In other words, all cells come from the original population of cells. These characteristics alone points us to in the matched cells analysis when we have the table of possible statistical tests. And we will go on knowing that we're going to be working with matched groups. In this case, we have more than 3, so we go to the appropriate cell. So let's now look at the sample size. We keep one well as the control, and we introduce 4 different treatments in each one of the other 4 wells. And all of them are subjected to the same treatment over 24 hours. In essence, we really only have a small sample size of size 5 because one subject is the collection of cells in one well. And with such a small sample, we can not talk about a normally distributed data, and we will again be looking at non-parametric tests. So going back to our table, having already established that we have matched pairs and looking for our options under the non-parametric tests, we'll find that the Friedman test is the appropriate one to use here. Again, we mustn't forget that this test will consider all 5 groups at the same time. As previously, if it is significant, it means that one of those pairs has a significant difference, but at this stage we don't know which one. So you would like to...
Yeah, how can I then compare the individual groups?
Okay. Again, we will be looking at 2 between groups. Again, we will be looking at between group comparisons, being able to only compare 2 groups at a time. So we are moving to 2 matched groups, and we will do a series of Wilcoxon matched pairs test. Again, the problem with Bonferroni, our old friend, we mustn't forget to do that. And let's have a look at the relationships that we have here, and we have many in this case. If at first we want to compare all the treatments to the control, so we will have a total of 4 Wilcoxon tests to do. We mustn't forget to adjust our p-value using the Bonferroni correction with a factor of 4. If we further want to look at the relationship between all the other groups, that will increase the number of relationships to 10, and we will have to use the Bonferroni correction with a factor of 10.
Scenario 3. This is an animal study, and I want to treat a group of animals with an experimental treatment or placebo. And then I want to monitor their blood pressure for a period of 4 weeks. This is how long the treatment period will be. And I want to see how the treatment affects blood pressure.
And you will be measuring the blood pressure at the beginning and at the end, or anything in between?
So I will have a tail cuff, and I will be measuring the blood pressure twice a day for 15 days.
Okay, thank you. Let's have a look at what we have. We have, again, one parameter, systolic blood pressure, which you said you would like to measure repeatedly. The reason why I've asked this specific question is because if we have one data point, it will be a different way of thinking our strategy. But if we if we measure it repeatedly, then it's a different way of considering the data to analyze it. So thank you for that clarification. Our population will come from 2 independent animal groups. So let's think a little bit about the design here. How are we going to allocate the animals into the groups? This is actually a typical clinical trial framework. The ideal way to allocate the animals from a pool will be to randomize them. An ideal situation would be if a third party was organizing the randomization and the researcher was actually blind to it. With randomization, each animal will have an equal chance of being assigned to any of the groups. So let's leave the randomization process to take place, while we'll talk about a little bit more about why randomization is important. For randomization to be successful, we should not be able to predict in advance the group memberships. There is actually quite a science behind randomization techniques that would also ensure that the resulted groups are balanced. I'd like to mention that randomization is actually a very broad topic and cannot be fully discussed in this brief session. So please bear in mind that I will only cover some of the very basic ideas here. And also as a reminder, if you are privileged enough to have access to a statistician or any other individual knowledgeable in this area, now is a very good time to discuss this with them. Although for illustration purposes we have completed the randomization, before we consider the sample size, in fact the correct order is to first think about the sample size and then think through the randomization options. The reason why we changed the order here is because we're going to be talking about the analytical options, and those would come after the randomization naturally. Going back to the sample size, you didn't specify, Harry, whether you have a small or a large data set. So I think I'm going to answer by giving all possibilities here. We talk about the larger groups and perhaps the smaller groups. What we need to remember, the clue here is, as we mentioned earlier, that these are repeated measures. So let's now first consider the scenario where we have a larger group, and that will be if each of the groups has 30 or more animals. Since we have a larger group, we have more of a probability of having a normally distributed data, so we will look at the parametric tests here. And the technical name of what you need to use is a two-way ANOVA for repeated measures with time versus treatment time, treatment interaction term, and we need this to check for between group measurement effects. I think that's probably beyond the scope of this short session to explain exactly how this technique works. And I would like just to repeat here that at this stage, perhaps a statistician is not a luxury but a necessity. If we look at the possibilities for smaller sample sizes, let's say we have less than 25, we're more likely to be looking at non-parametric tests, and one probability here will be to go back and use the Friedman test. But unfortunately that test does not allow for time interactions, so we're at a bit of a loose end here. And the other possibility will be to transform the non-normal data and then go back and follow the suggestions for the parametric tests. Again, a statistician will be very handy at this stage.
Scenario 4. I have a microarray experiment in cell culture. I have one intervention, so I treat half of my cells with a treatment, and then I want to test the changes in the expression profile of a large number of genes, let's say a few hundreds of thousands of genes. How can we do this in a reliable way?
So let's have a look at what we have. This is a microarray experiment, and these experiments tend to be quite expensive, and hence inadequate study design might actually prove quite costly, as well as having the disappointment of not having any results. These are also multi-step experiments, and here we will see very much an abridged version. So I would urge the researchers out there to explore the area in depth and approach someone knowledgeable in that area before attempting to plan any experiment like this. In such an experiment, we're usually looking to see whether a type of treatment, generally speaking, has an effect in gene expression. So we will have a well of cells formed by splitting, the main one. There are two ways to do this: a technical replicate and a biological replicate. The technical replicate keeps the treatment and the biology constant, and we are looking for repeatability information, whether the biological replicate on the other hand has more variability, as the biology isn't kept constant, and here we're looking for biological variability. Each technique has its own pros and cons, and there are maybe replicates using combination of biological and technical replicates. Without going into too much detail about the type of replicates we're going to have, we split here. We split it to obtain two more wells. Each would probably have thousands of genes, and we then have treatment versus nothing, with an incubation period of 48 hours. And at the end of that, we'd like to see if the treatment has an effect on gene expression. We need to note here that if there is an effect to be detected, it's very likely that more than one gene will be implicated. In other words, if expression on the gene is shown, that would probably trigger a number of other genes to react in the same or similar way, and so on. So statistically, there are rather a lot of issues one needs to consider. And the fact that these wells may easily contain hundreds of thousands of genes makes things even more complicated. So we're really not going to be able to do this using pen and paper. Adding to the fact that the microarrays are rather sensitive to environmental and laboratory conditions, we see that we are likely to need as many repetitions as possible in order to have robust results. There's a magic number that people use these days, and that's 3 for some reason. They think 1 is too little, 2 is better, but 3 is a lot better. Usually that's due to funding limitations, but obviously the more repetitions the better. So in summary, we should have as many repetitions as possible, and that gives us a number of complications. We will have, as well as repetitions, thousands of complex relationships to consider. And thankfully, over the last 10 years, and even now, appropriate software is being developed, and therefore we can rely on choosing the appropriate software to be done. So rather than considering the analytical strategy that one can do on their own here, I think it's probably better if we have a brief look, a simplified version, I should say, of the considerations of not of one analysis, but rather of perhaps the software developments need to take into account. First, we need, in essence, to realize that this is a hypothesis test. We're trying to explore the null hypothesis that there is no difference in the gene expression between the treatments that we're using. And I think that's probably the simplest element to start from here. Then we need to consider what tests are we going to be doing for the hypothesis. We're looking for gene expression differences. This is a continuous variable in that there is a measurable intensity of the gene expression. That's usually done by a scanner, and so it's a continuous variable, and a t-test one would have thought is appropriate. But we have many t-tests to consider, and the Bonferroni correction would run into thousands here. The issue of false positives is almost inevitable in so many different relationships that we have, so we need to remember that. The intensity here is measured by a scanner. So what the scanner does is goes over the array and picks up an intensity value. This is usually a skewed distribution, so we will need to think about appropriate transformations in order to obtain normality. Usually we would go for the log transformation. That's the most usual thing we do. So having said that would be the software that does it. And there are actually other assumptions to consider, because we have interlinked relationships here between the genes, and things are not easy. We will need to identify clusters of expression patterns to consider if they have been if the genes are co-regulated. So identifying the clusters in so many thousands of genes is not something that the naked eye could do very easily, but a computer can do much better, much quicker. Finally, we need to look for functional relationships among the differentially expressed genes in order to implicate pathways. To distinguish between which pathways are important to explore, we need to have defined an expected treatment effect beforehand, and if that is exceeded, then we move on to pathway analysis. And again, that computer can help us do that, the software can help us do that.
Scenario 5. In a translation study, I want to correlate the levels of two biomarkers, X and Z, with a third variable, let's say endothelial function, in a population of 100 patients, for example. Mm-hmm. How can we do that statistically? Okay,
let's have a look at what do we know. We have three parameters. We have a plasma levels of biomarkers X and Y, and a marker of endothelial function. So population will come from, did you say, a translational study? Presumably that would have been genes that showed some importance in earlier pairwise comparisons. And that kind of data is very likely to be continuous data.
Yes, this will be continuous variable.
Yes, a continuous variable.
All three variables are continuous.
Yes. So we are likely to be looking at a normal distribution if we're lucky, but we should explore that, and that's a good time to do that. We talked in part 2 of this podcast of the importance on checking and knowing your data. And we have many ways of looking to see if our data is normally distributed. So just a quick recap. If we have the mean and the median and the mode falling at about the same place, we can imply normality of the data. Otherwise, if they're not falling in the same place, we will have a skewed distribution, in which case we might consider the possibility of transforming the data. In terms of looking at the correlations, if we have normally distributed data, and we go back to our table that helps us decide these tests, we will see that we can look at a Pearson correlation. If we have a non-normally distributed data, we look under the parametric tests, and we will see that Spearman is most appropriate test. What I'd like to emphasize here, though, is that correlation does not imply causation. Many times we see this being confused in publications, and let me bring you a very simple example of how to keep those separate. On a hot summer's day, there's a very high correlation between the temperature, the outside temperature, and the number of ice creams being consumed. Correlation is very high, we cannot deny that. However, if we eat more ice creams, we cannot cause the weather to get hotter. So I think we can see how correlation, even high correlation, does not imply causation, and we need to bear that in mind.
Okay, and coming back to our experiment, our example, is there a way to compare the strength of the two correlations?
Yes, there is a way to do that. We can use the Z test, and I don't think this is the right forum to go in detail about how that is done, but I think it's widely available in all statistics books, good and not so good statistics books. So we can test that by taking two correlations at a time and using the Z test.
And is there also a way to test whether the two correlations are independent from each other?
Yes, we are venturing into more complicated areas here, but we could use a multivariable analysis in that case.
Probably you should call a statistician.
I think I was going to just say that at this stage, a statistician will be very handy. It's beyond the scope to go into the details of how that can be done. But yes, there is a way to do it.
Thank you. I hope you enjoyed this series of podcasts on basic principles of statistics in basic science. I would like to thank Professor Sir Rory Collins and Dr. Marialena Trivella for helping us with these podcasts.